Good morning, everybody, and welcome to episode 34 of our MakerBot Chats. My name is Felipe, and today we have an interesting one. It's going to be, again, a little bit more in-depth dive on metal 3D printing. Specifically, I just got a new round of parts sent back my way after being processed. So I'll be taking you guys through some of the issues that I've seen, some of the reasons why a few of these parts actually failed. And I have a fair amount of questions already submitted. And another additional one is we will be doing a quick strength test on the green part, so the part as it comes out from the 3D printer, versus the sintered part. Why is it important to sinter your parts? Why you really want to do that? And comparing that against ABS. As you can see here on the top right of your, top left, I guess it's mirror here for you guys, of your screen. I also have my test rig. I'll be using that to basically test the strength out of the 3 samples that I've got here. Let me center that out a little bit. Make sure that you guys are seeing it. But I've got an ABS sample, 316L green sample, so as it comes out of the 3D printer, and the final process sample, the actual sintered part that's metallic and has all of the proper characteristics. So with that, let's just get started with a quick overview of what does this process look like, right? Specifically, I want to show a couple of things. First off, the parts that I sent. So I'm moving the camera a little bit to begin with. Let me get some of these parts out of the way. To show you guys the parts that I've got here, and I have a few comments on them, kind of thoughts on why some of them perform a specific way versus another. Overall, I'll say I have 6 groups of parts. First off, I got this quick fan prop component. I got a gear here, a set of hex keys, 2 different 15mm keys, just the tip of the key actually. Refocusing my camera. A quick texture test here, and finally just a more uneven geometry with this 3-way pipe or 3-to-1 sort of pipe adapter. I'll be switching back to my macro shot, which should also enable us to have a nicer view of these parts. More sort of, sorry about that. Here we go. So a more detailed set of shots. I'll take you through each of these parts, what I was looking for with each of them, and then we'll talk about kind of what was the processing process, the post-processing process actually, how I sent the parts. Let's try and get these to focus. There we go. How I sent out the parts, the issues that I encountered with each of them, and then sort of learnings so that you don't have to go through this process on your own later on, right? Starting with this fan blade. With this one in particular, I was kind of looking to challenge a little bit of overhangs, and also looking to see how thin a geometry I could make, specifically with that geometry being a little bit more organic, right? It's not to say that the propeller is completely organic, but you can see how these sort of complex surfaces do challenge a little bit of the metal processing, the metal process. As you can see, out of the 7 blades, 2 of them failed. The reason for that, and we covered a little bit of it on a previous webinar, is because I'm really flying really close to the edge of what's possible with the sintering process, right? And interestingly so, when you process your parts, when you send them out for sintering, you do get like the full set of the parts. So even I got back even the little chunks that fail, and I think that gives you a really good understanding, a really good idea of why the part didn't process as expected. We'll go through the processing ticket in a second, but yeah, so this is kind of one of the most challenging parts that I sent out. Each of these blades had a thickness of about 2 millimeters, so fairly thin, fairly complex structure. As you can see, like there's quite a bit of an overhang here at the beginning of the propeller, and there were no supports there, right? So that's one other reason why this part might have failed. We'll cover more of that in a second when we go to the processing ticket. Second one, very standard gear piece, really nice finish actually. The more and more we test out this material, the more and more we realize like even parts have the highest rate of success, right? These sort of thin, flat, even round shape, it's just really easy to both print, process, and get a successful output out of it. So really nice finished part here. You can see all of the details are really nicely kept. As we've said before, even the zipper line, let me try to get it here. Here we go. Even the zipper line is captured there. Had I processed the part a little bit prior to sending it, and what I mean by that is, had I sanded it off a little bit, probably most of that would have been gone away. I haven't really tinkered with that with it that much, meaning with pre-processing the part, just because I want to get comfortable with the material first. But yeah, essentially really successful part here. Moving on to this three-way pipe. I'll leave the nuts to the end, but this three-way pipe, also a fairly organic shape. The main reason for this part was just to test out a little bit more, pushing the envelope on overhangs, right, and more complex organic geometries. You can see how nice the part is finished inside. It's the surface finish is great, I would say. All of the details are there. Again, the zipper line really visible. I think that it would be a really good idea to just sand it a little bit prior to sending it out. I think that could definitely help with even smoother finish, but already you can see how great a finish that is, right? It's like a really even part. One of the issues with this part, however, is that the three valves, right, coming into the pipe are uneven in size. And as you can see, I've got 2 smaller circles and 1 larger one. What that in turn caused is a little bit of an uneven deformation. So going back to that idea of the more even your parts, the easier it will be for you to post-process it successfully, right? So essentially what's happening here is the material is shrinking towards I would say, this is not technically accurate, but kind of towards the center of mass, right? So in a way you can see both the circles are being pulled closer in. I'm hoping that you guys can see I'll stop moving or shaking the part that much to make sure that it's a little bit more obvious. But if I place the part dead on, you'll see how these circles are sort of squished towards the center, so they became an elongated ellipse on, say, the z-axis as it's presented towards the camera, whereas this main circle, or the bigger one, got squished like so, right? So essentially pulling the outer wall into the part. So again, as we've discussed in the past, all of the sintered parts will have some level of shrinkage. How much, how little? It's about 20% on X and Y, about 26% in Z, but it changes and it varies a lot in the part, right? The more even your part, as what happened with the gear, the less or the more even the shrinkage rate that you will have. The more uneven the part, as what's happening with this more organic shape, the more uneven the shrinkage. However, the part is fairly flat, well, actually not fairly flat, it's really flat. That sort of property stayed there. It's mainly that shrinkage on the circles that's what's challenging. Now, there's a few pieces of software out there that we'll recommend in the future that will help you evaluate how to scale up your part, how to make sure that it's kind of the closest that it can be to the actual spec. But that's definitely something to keep in mind, especially for uneven parts. On the one hand, it's really great to see how we got a really successful result with these bridges, no supports here, really smooth surface, really smooth finish, but an uneven shrinkage due to, in fact, the shape of the form, the shape itself of the part, right? Next up, this was just a quick texture test. I wanted to see, again, testing out overhangs, testing out more uneven geometries. And in this case, because this is just an aesthetic test, there's really no noticeable, massive deformation, right? It's a fairly even part. It just shows how smooth the texture can be. You can see those dimples that I created were simply respected. There's no supports here, and the part came out actually looking great, right? Really nice surface finish, really nice part. I can of course sand this part. I will probably do so and get it to a mirror finish if possible. I'll keep you guys posted, like what happens once I try to sand off all of the layer lines, but this is essentially now solid steel as all of these parts are, which means that I can probably just process it in the same way that I would, a simple piece of steel. And the final set of components before we jump into the strength test is going to be these two nuts, right? They are going to be essentially, or they are designed to essentially interface with the same size of a nut, 15 millimeters. However, the design choices here really do matter. As I said before, both of them are meant to interface with the same side of a nut, but one of them, as you can see here, presents a complete open ended side, right? It's kind of like to go into the nut like so. The other one would just go like from top and into the nut. By having an open side, you can see how this part deformed a little bit, right? You can see how let me put it straight into the camera, how the last bits here flare out just a little bit, right? Now let me put my hand on the other side, but just enough. It's about, I've measured it before, but it's about 1 millimeter. Like with that view, actually, you'll probably be able to see it more, how it's sort of flaring. Let me tilt the camera more. How the part is flaring, right? There you go. So it's flaring about 1 millimeter. The reason for that is, as I said before, the part will deform towards, I feel like I would like to describe it that way, right? Like just the center of mass of the part. Whereas this part that is completely even, the result, it's just outstanding, right? The part is really nice, really great surface finish. The details, the teeth there are really good. And essentially it goes to, show how important are the design decision choices, the engineering choices that we make when using metal, right? Because essentially both parts will do the same job. One of them is a little bit more challenging to print and should accommodate for that deformation to happen because of the unevenness, right? Because of the inherent uneven shape of the part, that will in turn cause or can cause shrinkage in an uneven way, right? I'll stop it here and I'll take you guys through my processing sheet, which is also a really interesting thing to note, right? When you send your parts out to, in this case, to matter hackers for them to post-process, in our case, we were, these parts are sent out to a processing facility out in New Jersey, basically across the river. We're located in New York and Manhattan. But it's great to see kind of the, the documentation that you get with the parts. So it's not only that you're sending out your parts and sort of getting something back in the mail, but rather that you're sending out the parts and they will be documenting every step of the process, right? Kind of telling you, okay, this is how we got the parts. So this is essentially what I'm showing you guys here. They'll take a photo of the parts and how they arrived in the first place. So you can see they even have this checkbox for in case any of the parts come in damaged. It's also great to know, which would be kind of like a user error. That didn't happen. Then they will document each of the steps, right? Basically laying out the parts as green parts prior to the debinding process. First step here, and this is actually the brown part. So like the first step covered in processing the parts. And after that process was completed, here you can see for the first time how this blade failed, right? So the blade itself failed prior to sintering. It failed during the debinding process. They actually, documented nicely, like a close-up of that part, the actual reasons for the failure. So failure had a fairly, the part had a fairly big overhang. That's one of the reasons. Then the thin wall might have also contributed. As I said before, these are about 2 millimeters across. So fairly thin parts, really close to the limit of what's possible with metal, and specifically the combination of the thin part, the thin walls, with the overhang, right? Ultimately caused this failure. As I've been asked before, one of the weird things to note, it's not weird, I think, but it's one of the things to note is the fact that this part has 7 blades. Only 2 of them failed. So why is there a discrepancy? And I think that the simple reason is that I'm just getting too close to the limit without crossing it, right? So say almost 30% of the blades fail because I'm really that close. If the part had been a little bit more aggressive, a little bit thinner, probably I would have seen many more blades failing. In the same way, if I make them just a little bit thicker, I will probably be fine, right? So I'm just kind of really close to finding the limit of what's possible with this overhang and thickness combination. Moving on with the rest of the parts, this is actually the final sintered photo of the parts, right? As I said before, as I mentioned before, it's nice to see how they do a great job at documenting each step, even collecting the little bits and pieces of the parts as they fail. I think that that's really useful from my perspective, kind of to learn a little bit more on the reasons why, have a little bit more exposure on, or being able to understand. I think that it's always as important as the result, is understanding why that result came to be, why that part failed. And yeah, so that's essentially it, right? That covers all of what you would get. This ticket is sent to you once the parts are sintered. You get this nice PDF covering all of it and basically documenting the process, which I think it's great to see. I'll jump now into, here we go, second bit of the video before we jump into more like detailed questions. But just, we've been hearing a lot of questions around the green parts versus the sintered parts, right? What is the risk or what is the benefit of me, let me work with this setup a little bit, but what's the benefit of you sending out the parts for sintering? I want to make sure that you get like a clear view of the screen here, so it's now in zeros. But what's the actual benefit of sintering the part? How much does it change in regards to the actual behavior of the part, right? So for these, I have three samples that I printed out on the same machine. So these samples are all printed on a method. I've got an ABS sample. I've got a green part, trying to move my finger out of the way. A green part, basically how it comes out of the machine once it's printed, still metal. And I've got a sintered part, so the same part. These are actually exactly the same parts. This is the green part, this is the sintered part, but essentially the same part before and after. You can see how the part is actually shrunken a little bit, right? There you go. So green part versus sintered part, and then comparing that against ABS. So let's just do a quick test. I'll just write here ABS, green, and sinter. Here, sorry. I just got my very handy post-it note there. I'll start loading the machine with the first part. This is an ABS sample. It's about 2 millimeters, if I'm not mistaken. I think it's 2.5 millimeters, the height of it. Here we go, just measuring that out for you guys. Yeah, 249. That's also true for the green part. Oh, running low on battery here. Let's see. 2.5 again. And then the sintered part is going to be a little bit smaller because, as we've discussed before, it should have shrunken. So I'm guessing this is going to be around 2.2, but we'll see. Oh, look at that, 2.2. Sorry, I haven't measured that before. But in any case, I now have the actual dimensions. As I said before, sintered part is the same as the green part, just after the sintering process has been taking place. I'll go ahead and load my ABS part. This is a very thin part, so I'm not expecting it to have, a massive amount of strength. And of course, loading my goggles as well, safety first. Okay, you guys can see the 0, 0. Cool. So ABS part is loaded. It's a very thin part. You can see it here. And let's see how it sort of fares against the test. Let's start. ABS sample, test 1. That's 20 newtons, 50 newtons, 60 newtons, 68. There's a peak load of 68.5 for ABS. So I'll just document that here. 68.5 newtons, right? Peak for ABS. Let's unload this part. And while I'm at this, just feel free to ask any questions in the live chat. Also, if you're looking at this as a recording, you can always comment those questions out in the chat section down below in YouTube. We'll be sure to answer those either on the chat or on a later episode for sure. I'm going to go ahead now and load my green part, resetting my unit, my test unit. So green part, this is the part as it comes out, the metal part, 316L, as it comes out of the machine itself, right, of the printer. Loading the part, resetting the rig, here we go. You guys can try and guess. So ABS was 68.5 newtons. Let's see how the green part fares. So green metal, test 1, 16, 18, 19, 20. There we go. So peak of 20 newtons and the part failed, right? So fairly brittle part, the green steel itself. Kind of chewy, I would describe it that way. You can see how the part is completely solid, so there's 100% infill there. But, not a lot of strength on that part itself. So 20 newtons for the green part. So green, 316L, just to be sure that we capture that appropriately. It's almost a third of the strength of ABS. So green parts for metal, green metal parts, not there yet. You should really pick, there's a reason why the sintering process is going to be useful. So last test or final test before we run into or jump into the questions, sintered part. So loading the part here in the rig. It's going to be a tight fit. There we go. Resetting the rig. And again, this is the same metal part, that just did 20 Newton result, but after the sintering has been applied to it. So let's go ahead and test it out. And this is 316L part sintered. 20, 70, 100, 130, 200, 260, 300, wow, 350, 400, oh wow, 460, 480, 500 newtons, and still going. That's the limit. I'm approaching the limit now. 500 newtons. I don't want to push out the machine anymore. That is actually the limit of my force gauge. 500 newtons, peak of 510, and the part is still there. I'll bring you guys a little bit closer. There's a little bit of a deformation, right? It's flexing a little bit, but that's 500 newtons. So at least, let me reset this before I completely destroy the rig. 510 newtons. That's crazy. 510.5 newtons. Here you guys can see the actual peak load here in my rig. Hopefully you're being able to see that, even beyond the glare. So these are the final results. ABS, 70 newtons, that's a peak load. The green, that's 20 newtons. And the actual sintered part is 510 newtons, at least, right? But just to know, this part didn't actually fail. The part is still there. It's just, I've reached the limit of the test rig. So 500 newtons on the sintered part versus 20 on the green part. I'll leave that part, the post-it note there, super useful. But you can see how much difference this make, right? How big a change, jumping back here, how big a change it is to actually sinter your parts, because we keep getting a lot of questions on, well, can I just use the green parts and skip the sintering process? The answer is you really shouldn't. You're not getting what you are paying for by just printing the green part. I mean, there's a reason why the sintering process is there, and the reason is mainly, well, to actually get you the metal results, and those results are just incredible, right? It's close to 10 times as good as ABS, and it's about 40 times as strong, and this isn't without taking the part to its failure point. But almost 40 times as good as, 20 times as good as the green part. So really, really important to get those parts sintered. And with that, I'm going to go ahead and jump into the question section here. I'll bring the camera back into my parts, just in case you guys have specific questions on some of them. Here we go. Okay, and looking at some of the questions that we have collected throughout this session. So are we just jumping into my questions document? Here we go. So how long does the 100% infill print of something like this turbine take? This propeller at 100% infill took about 11 hours to print, if I'm not mistaken, so it's not a lot. Basically an all-day print. How much wear does this material create on the print heads? I would say the answer is that these print heads are meant to withstand that wear. That's why we're using the lapse extruder, right? The lapse extruder has many hardened parts between, the gears themselves that drive the material, the actual nozzle that's also steel as the rest of the nozzles, and the detection switch, which is also steel, hardened. So it doesn't really damage the lapse extruder, but that's kind of the reason why we're using the lapse extruder, right? That's a very easy to replace part if there was to be any wear. Weldability of the 360 material. I haven't welded it yet, so I don't have an answer for that just yet. I'll be looking into that in the future. Is the 2020-26 shrinkage specific to the 316L stainless steel? Yes. So as I mentioned before, these parts, from the green part to the actual sintered part, will shrink about 20% in X, 20% in Y, and 26% in Z. That's about, right? That's a ballpark estimate, and it is just related to this specific material, the BASF 316L. What are the tolerances between the final sintered print and the original 3D model? Does the slicer compensate for shrinking or expanding during the sintering? The answer is no, the slicer does not compensate for the shrinkage. You have to actually input that yourself. We give you the guidelines, so that's the 20, 20, and 26% that I mentioned before. And the tolerances, overall, I would say that as long as you're operating within 400 microns, you should be fine, even 200, depending on the shape of the part. So as I said before, or as I shown you guys with these parts, the design itself of the part will have a lot to do with how much it distorts and how even the shrinkage is. So the more even your part, the more control that you will have on the shrinkage rate itself. Porosity of the parts, these are solid parts. I need to sort of print basically a block and compare the density of both of them. I think my understanding is that the density is about 95% of a solid block of the material. So yeah, resistance to water under pressure, that's also pretty good, but you would need to test it out. And it depends on the part. There's a lot of variables there, right? How thick are your parts? How big are the walls? So there's no straight answer to that. I'll just do one more question before we run out of time. And yeah, would it be appropriate for low volume automotive production? How does the final part cost compared to metal injection molding or traditional casting? So I would say probably yes. It all depends on the part that you're trying to print, right? It all depends on what type of part are you looking to create. If it's a very, very complex part that needs very tight tolerances, maybe, I don't know. If it's a fairly simple part, you're trying to replace some sort of gear, some sort of connector, you would probably be better off with printing it than casting it or injection molding for two reasons. First off, timeline. Second, the pricing itself. This part is gotta be worth, I would say, I don't know, maybe like $40, about $40 in material and processing. And the good thing about the processing ticket itself is that even though it's an added expense, when you divide the processing ticket amongst all of the parts that were sent out to the sintering place, you end up getting like $5 per part for sintering. So that's not too bad, right? But yeah, so with that, I'm going to thank you guys again so much for joining us this morning. It's great to see you guys here. It's had been a while, I know. But yeah, as always, thanks again. We'll see you next week, same time next week. If you have any questions, don't hesitate to reach out either at MakerBot on Twitter or Instagram, or either one of our emails that are shown there. hello@MakerBot, Felipe, Felipe @MakerBot. But yeah, until then, I'll see you next time. But thanks again for watching. Bye.